Welcome to the shape of space matrix calculus first derivatives. In this lesson we're going to use some of the concepts from the previous lesson where we modeled derivatives as linear operators, and we're going to take first derivatives of various scalar valued, vector valued, and matrix valued functions. And then in the lesson after this we'll talk about second derivatives. If in equation 3, which I copied for us up here, we let u be Rn and v be R. That's really not in equation 3, but in the Furchet definition of a derivative. We're just going from a vector to a scalar. That's all that's saying. It's just saying f is scalar valued. So it takes in a vector and it puts out a scalar. And we replace dx by the dual number epsilon dx. Then this term here that has all these higher order terms with epsilon dx is going to go to 0, and we get this equation here. In the above, df is a scalar, x and dx are n by 1 column vectors. The derivative f of x is a 1 by n row vector. And we already know from the previous lesson, several lessons back, that the gradient, this thing here, is a solution, and we know that the Furchet derivative is unique. So in other words, this is a solution. The gradient is a solution to this equation here. And I'm just drawing out what I stated in this paragraph. X is a column vector, dx is a column vector, and then the derivative is the transpose of the gradient. If you recall, the gradient was a column vector, but we need to multiply that times a column vector, so we need to convert this to a row vector. So the gradient is one approach, and we saw a few examples of that for determining the derivative of a scalar valued function that takes a vector as input and outputs a scalar. Another approach is to compute this quantity here, which I'm going to show in a few examples. Let's look at an example using the linear operator approach based on the definition of Furchet differentiation in our equation number 4. So what we have here is a function, the scalar valued function. It takes a vector and it outputs a scalar, so we call that a scalar valued function. And the definition is A transpose X. A and X are elements of Rn, so they're both vectors, and A is a constant, and X is a variable, or a collection of variables, x1 to xn. And we want to determine these three quantities. So we'll use our equation here, we'll compute this, and then whatever we get, if we can get it in this format here, we can just read off the derivative. It's pretty easy. We plug in x plus epsilon dx into this. We get this here, and subtract f of x. And you notice the first term and this here cancel, and then you just get A transpose epsilon dx. And compare it to this here. So what's here, the derivative of f of x, and it must be this thing here, A transpose. So that gives us our derivative, and then the, this is also, we also have df. Then the last thing we needed to compute was the gradient, and that's just the transpose of the derivative, so we get A. So pretty easy using our linear operator approach. If you wanted to do it using the gradient approach, you would have to give the elements of A names, A1, A2, up to AN, and then the elements of X names, X1 up to XN. Multiply these together, then take the partial derivatives to get the gradient, and then you'll see that what's left is A. So it's more work, but it's another valid approach. We have another example here, f of x equals x transpose ax. where A is a constant n by n matrix, and X is a column vector, and of course X transpose would then be a row vector. So you have a 1 by n times an n by n times an n by 1, and that gives you a 1 by 1 output. That's why we call this a scalar valued function. It takes a vector as input and it outputs a scalar. And we want to find the differential, the derivative, and the gradient. So we'll use our equation 4 based on the Fouché derivative here. We'll use the dual number version of it. So we plug in x plus epsilon dx into this, and then we subtract f of x. Then going from here to here, all I did was take the transpose, which I'm showing here, and keep in mind that dx is also a column vector, so this is a row vector here. Then we need to multiply this out, and keep in mind that when you're working with vectors and matrices, they're not commutative normally, so we have to keep these in the right order. So it will be x transpose times a times x, be that term, and then x transpose times a times epsilon dx, and so forth to get these terms. We can move the epsilon around, which I've done in here, but the vectors and the matrices need to stay in the same position, the right order that when you're multiplying. So I multiplied this all out, and I carried this over. Then this cancels with this. This is an epsilon squared, so we know that's 0. So we're just left with these two terms, which I brought down here. Then we have a bit of a trick, which I didn't see initially. It took me some digging to figure out how to get from here to here, but it's actually quite simple. Dx transpose is a row vector, then times an n by n matrix times a column vector. So this is actually a scalar. These three things multiplied together are a scalar, which means that they equal, the transpose of a scalar equals itself. So this equals its transpose. And I just carried over the first term. Then I actually took the transpose of this. So remember, the transpose of a product is the product of the transpose of each element, but in reverse order. So it would be x transpose times a transpose times the transpose of dx. In other words, this here. Then you can factor the x transpose out to the front. You can move the epsilon anywhere you want. In this case, we'll multiply times the dx and factor that out. And that leaves us with a plus a transpose. So this is a differential. And we know that what's here multiplied times epsilon dx is the way we constructed our formula here from the Fouché differentiable function, that this is the derivative. Then the gradient's a little bit slippery. I'll explain in a second. It's the transpose of this, so it's the transpose of these terms in reverse order. So I take the transpose of this times the transpose of x. So this looks normal, but why don't I have a transpose plus a here? Right? It should be that, but it turns out that for any square matrix, the matrix plus its transpose equals its transpose plus itself. So that's what I did. I just substituted in. This is the reason I did this is the normal form that you normally see if you look this up in a book that has derivatives of matrix and vector functions. I could have left it this way here, and that would be fine. Okay, now if you use the gradient method, and actually I went to one of the AI programs, DeepSeek, and I asked for the derivative of this, and it actually used the gradient method, and it just went on and on and on with very complicated summations and formulas. Basically, you have to label all the elements of x and x transpose and then all the elements of A, which is a matrix, and multiply that all out, and then take partial derivatives, and then eventually you'll notice that the derivative is this pattern here. So it's much easier to go this way. I have a few more examples of scalar valued functions, which I'll show you on the next slide. Given a function f of x equals a trace of x, where x is an n by n matrix of real variables, determine the differential of f and the derivative. For the differential, we'll use equation 3. So we have this here. Then the trace of x plus dx is just a trace of x plus a trace of dx. And so this cancels the first term, and you get just a trace of dx. The derivative will compute we'll get the derivative by computing the partial derivatives directly. So since f of x, being the trace, just equals the sum of the diagonal elements, xii, where xii is just the ith diagonal element. The partial derivative of f with respect to xij is 1 if I equals j, in other words, if it's a diagonal element because of this equation, and it's 0 otherwise. Thus, the full set of partial derivatives of f can be represented by the identity matrix. So that's pretty straightforward. What's a little bit different is this is not exactly the gradient, since the gradient is defined for functions that map from Rn to R, and the trace maps from the vector spaces n by n matrices to R. So what we have is sort of a two-dimensional gradient. I'm not sure there's an official term for this, but I just call it a two-dimensional gradient. And you may think, well, that's the Jacobian, isn't it? Well, no, the Jacobian is defined for functions that map from Rm to Rn. So that's not what we have here. This type of two-dimensional gradient is needed in general when we have a function that maps from matrices to scalars. And we'll see that also in the next problem. Our next problem is to find the differential and the derivative of the function f of x equals determinant of x, where x is an n by n matrix of real variables. The differential of f can be expressed as the sum of the differentials of f with respect to each variable in x. That's why I have an ij here. And the formula is given by this, the sum of each one of these. And then each df ij is the product of the partial of f with respect to xij times dxij, which is the differential of xij. So as was the case with the previous example, we need a two-dimensional gradient to represent the derivative of f of x, which I'll get to on the next slide. For the determinant function, of course, we need to actually compute what these things are, and we're going to use the cofactor matrix. If you're not familiar with the cofactor matrix, I have a video in my previous series on matrices that talk about that. We're going to use a formula related to the cofactor matrix. It's this that I copied down here. So for each column of x, we can express the determinant of x in terms of the cofactors for the different elements along that column. And then these are just the elements in the column J of our matrix X. Okay, so the formula is here. We have the determinant, the partial determinant of x with respect to xij. So we just find the appropriate expansion for the column we want to work on. We do that for each column, and then we see that everything's going to have a derivative of 0, partial derivative of 0, except for the ij term. So for example, if we wanted to take the partial derivative of the determinant of x with respect to x to 1, we would use this column 1. Then you would have a 1 here for all the j's, and when you take the partial derivative, everything is 0 except this term here, which it just gives us c to 1. And you do that for the entire matrix X, for every variable in matrix X, and you get Cij. So all these partial derivatives give us a matrix, which is the cofactor matrix. The cofactor matrix is by definition, is the inverse of something called the adjugate matrix, which I have written down here. You notice I have the ij and ji in reverse order because one is the transpose of the other. Okay, so we need to continue this on the next slide. So carrying over from the previous slide, we had this equation, and then we found what this was the ij cofactor, so I plugged that in here. And then conveniently, this can be written as the trace is the adjugate of x dx. And for going from here to here comes from this formula, which I think I mentioned in a previous lesson from the last series, but I'll mention it here again. So the trace of A transpose B is this double summation of Aij, Bij. So that's what we have here, Cij dxij. And so what we need to put into the formula here is the dx, but then the transpose of this, by definition, the transpose of the cofactor is the adjugate matrix. So we have our solution here. Further, since the adjugate equals the determinant of x, which is a scalar, times x inverse, when x is invertible, then we can write the following. We just take our formula here, plug this in, and then we can factor out the scalar, and we get this equation here. For the problem at hand, the derivative f of x is the matrix that represents a linear transformation df with respect to dx. In matrix calculus, when f is a scalar function of a matrix x, in other words, a scalar output, matrix input, the differential is often represented in this form here. df equals the trace of the transpose of this gradient dx, where nabla f is the derivative. So we can make this identification using either this formula, or when we have an inverse, using this formula here. Let's use this one here. So from the first expression for df, this here, we have that the derivative of f equals the transpose of the adjugate matrix, which is by definition is the cofactor matrix. So this is one representation for the derivative of the determinant. And then if x is invertible, then we can use this other result here, and it would just actually, let's look at it in here before I factored out the determinant. So it would just be this, and then you'd have to take the transpose of the inverse. Okay, so really not so easy. You would think maybe the determinant of the derivative of a determinant is simple, but keep in mind that the determinant of a matrix full of variables is not a simple thing. But the answer, once you get through all the work, isn't so bad. So we get the differential is this kind of neat equation. And if we have a x being invertible, we get this, and then that just carries over to the derivative. We can apply our approach using the Furché derivative to functions that take a vector input but also have a vector output. In other words, from Rm to Rn. And we start with our equation 3, and we make the substitutions we've done before, so these higher order terms all go to 0. We have this here. So this is similar to what we've been using in the previous examples, except the previous examples had a scalar output. Now the output is a vector. So df is a vector, and f of x is a vector, and x is a vector, and dx is a vector, and then the derivative is a matrix. So I wrote that out for you down here. X and dx are column vectors, and the derivative is the Jacobian matrix, this thing here. So our approach is that we'll find the differential using this formula here, and then we'll try to work it into the format of like this on the right, and then we know that what's here multiplied times epsilon dx is the derivative, and not only is it the derivative, we know from the theorem related to the Fauché derivative that it's unique. Okay, so we'll do a few examples of this, and it'll be the rest of this lesson basically. On this slide I have a couple of examples of where we have functions with a vector input and a vector output. The first one is f of x equals ax, where a is a matrix of constants, and x is a column vector of variables. So we use our formula here to find the differential. We just have a times this minus ax, and so you get ax here and minus ax, that cancels, and then you get a epsilon dx. So this is our differential, and then we can just read off the derivative, it's a. Kind of what you might have guessed, since it looks a lot like basic calculus where you just have single dimension variables here. You're taking the derivative of a variable and then you're just left with the constant. Then I switched things around a little bit in the second example. It's the same format, f of x equals a matrix times a column vector, but now the matrix has variables in it. So it's an n by n matrix of variables, and then a is a constant vector. So far it looks exactly the same. We plug in our information into the equation here. You notice we have a capital X here now because it's a matrix, and that's what's going to complicate things. So we multiply this by a, and of course the xa and the xa here cancel, but then you get epsilon dxa, and we can't change the order of this because matrices and vector multiplication doesn't commute. Matrix multiplication doesn't commute, so we're kind of stuck. But there's a solution to this. We have an equation from Theorem 72, which I've copied down for you here. The vectorization of A, B, C. These are matrices, although C could be a column vector, which is the case we have here. It equals this, and you notice this shifts things around in the direction that we need to solve our problem. So we'll take the vec of dxa, we'll multiply by I, so the identity matrix, so this is the same as this. I did that because I want to get three things here to use our formula. Then we apply our formula, and as I mentioned, if this last thing is a column vector, it still works. So we get A transpose Kronecker delta with the identity times the vec dx. Thus we have that the vectorization of df, our differential, equals this here. And you can move the epsilon around wherever you want. So this is kind of in the format we have. And so it then follows that the derivative, f of x, equals A transpose Kronecker delta with the identity matrix when expressed as a matrix acting on the vectorization of dx. I have a few more examples here, but in this case the output from the function is actually a matrix we can handle that by extending our formula for df. It looks pretty much the same here. The output will be a matrix, so f of x is a matrix in this case, and our dx term is either a scalar, a vector, or a matrix, depending on what the input is. And we can either use this form that has the dual number, or we can use it without the dual number, and just remember that all the higher order terms, the dx squares and dx cubes, need to be eliminated, and we can use this second formula if we like. And in fact, I believe I used that in the second, well, actually I used it in this first example and in the second example. So we want to, oh, I need to make a correction too. From 2 videos back, I believe I said the product rule didn't hold for the differential related to the Fauché derivative, but it does hold for scalar functions that have a scalar as an output. That's just regular calculus. And it does hold in the case where you have a matrix output. So those 2 cases work. In the case of vector output, I was correct in saying it doesn't hold in general, but even there, if you define the vector product as being the dot product or the Hadamard product, then you can make the product rule work for vectors. So with that correction in mind, I want to use the product rule here. We have f of x equals x cubed. We want to find the differential and the derivative, but x is a matrix of variables. It's not just our simple calculus case here. So we're not going to get 3x squared for the derivative. We'll get a more complicated expression because the matrices don't commute. So first we'll break this down into 2 parts. First we'll find the differential for x squared using the products rule, and we'll look at this as x times x. It's just the first times the derivative of the second plus the differential of the first times the second, I should say, so we get that. And then we move over to x cubed. We write that as x squared x. And then we use the product rule here. We get x squared times the differential dx plus the differential of x squared, which we've computed up here, times x. We just carry the first term over, and then we substitute this in for dx squared, which I put here, multiply by x on the right, and we get this. So that's our differential for x cubed. You notice it looks almost like 3x squared dx, but we can't commute these things necessarily, so we're kind of stuck with this formulation. Now we want to pull out the derivative, and so we want to get the dx to the right, and so we can read it off. We only have it in the correct position here, so we need to work on these. And what we can do is use the Theorem 72 as we did in the previous example on all 3 of these. Actually, I could have left this one out, but I did it on all 3 of them. So we apply this. You notice the dx is in the middle in each case, so that's the b. That comes out as vec dx. And then what you have for each of these terms would be I transpose, Kronecker product was x squared, plus x transpose Kronecker product was x, and then x squared transpose Kronecker product was I. And so we have this expression here. And this, as you recall, was the kind of the format we had in the previous example. So the way to interpret this is that f of x, the derivative of f of x, I should say, equals the Kronecker product of I was x squared plus x transpose Kronecker product was x plus the Kronecker product of x squared transpose was I, the identity matrix, one expressed as a matrix acting on vec dx. Okay, so not pretty, but that's how it goes when you're working with matrices. Even something that looks simple, you can get a quite complicated expression for the derivative. And there's actually several sources where the Derivatives are listed. I believe there's a Wikipedia page, and there's a document that has just pages and pages of derivatives. So you don't need to do this in every case. You can typically look them up, and I'll give you the references to those in the link, links to this into this video. We have one last example in this section. We want to find the differential and the derivative of f of x equals x inverse, where x is an invertible n by n matrix of variables. We know that x times x inverse is the identity, so we'll take the differential of both sides of this. The differential of I being a constant is 0, and then the differential of x times x inverse we can get using the product rule. It's dx times differential of the first times the second, then the first times the differential of the second, and then we can just multiply by x inverse on the left and then subtract to the other side to isolate this term here, and we get this. So that is the differential of our function df. We need to use theorem 72 again in order to isolate this dx and get it to the right, and then read off our derivative. So I copied that down here for us. So we have these three identified with A, B, and C, and then it would just be and bringing the minus over. So we'd have x inverse transpose Kronecker product with x inverse times the vec of dx. And then that means that the derivative of f is minus x inverse transpose Kronecker product with x inverse when expressed as a matrix acting on vec dx. So that is it for this lesson. The next lesson is on the second derivative and something known as the Hessian matrix.